I mean, come on, you never know. So that's a possibility, right? Same kind of idea though, correct? You have four somethings and then you have one extra something and then you put them together and there you go, right? Yes.
Like say kind of in the drawing circles or tally marks.
Tally marks, okay. I like it.
Yeah, kind of 1, 2, 3, 4, and then draw one.
Got you. So does everybody agree those are kind of like all the same kind of idea? So you have a visualization. You can have a physical visualization of four candies. You can have a drawing of four pieces of candy. But there's sort of like two sets of things that you're combining, correct? Does anyone feel like they have a different than that approach? Yes. Number line. I love it. So on the number line. I like it. So you can represent four. You got one more space. Yes, that's what's called the measurement model. So don't worry, I'm going to get all notey on you in a minute. But we got the set model, which kind of makes sense. You just have sets of things. You have the measurement model, which is primarily a number line kind of idea, but we'll talk about some other stuff for measurement model. There's another one about just the chant, right? It's the idea of counting by one. So if they know how to count 1, 2, 3, 4, 5, and you say, okay, what's 4 plus 1? You just go one more step in the chant. And that's sort of like different from everything else. A little bit like the set stuff, but I don't have anything physical or visual. It's just the chant, right? Yes?
Oh, that's what I was going to say. Usually, if I'm doing homework with my kids, I usually say, like, if you have 9, and then what's 4 more? You know, obviously, they only have 10 fingers, so they go 9 and go add 4 more, and then they go 9. And they do it with the rest of the things. So they usually start off with the biggest number, and then add.
Yes, so you count on from the biggest number. Yes. And the nice thing is, once you get to 10, then you can tell them, like, the 0 becomes 1, and then it has an internal count. Does that make sense? So if I got to count 9 plus 4, one of those makes 10, and then 1, 2, 3 for the second spot. So you get 30. Yeah, okay. I like it. Sweet. Okay. So as always, we've got a visual way of doing things, which kind of leads to the computational way of doing things. So let's see. Okay. By the way, I'm kind of excited. I think I told you this. So I'm going to get an iPad. I've got it coming. So I'm going to try to wirelessly connect to this so that I can walk around the room and just write on my iPad. And the nice thing about that is I'll be able to save the damn notes and then put them up on Canvas. So you'll have the video on YouTube and you have the notes from lecture. And because my desk at the end of class, I have just papers just everywhere. It's insane. And I don't like that. So today's the last thing I'm going to do that probably. So with addition, we've got the set method. So if I have like 2 things, and I have 4 things, which bunch up? Sure. Sure. Okay. I can physically put them together into one pile. Sure. And then you can have the student count 1, 2, 3, 4, 5, 6. So I need you to realize how many levels of thing is happening here. They can memorize 2 plus 4 is 6. Just like you can memorize je vais à la plage means I go to the beach, right? You can internalize the fact that 2 and 4 I can just count. 1, 2, 3, 4, 5, 6. I can count the result at the end. I mean, so for something so basic, it's only basic because it's a long time ago that we learned it. There's not a damn thing basic about this. So when you have a little blank slate of a little human being, they have nothing to ground themselves on. So this is a lot for them to get. Okay. The nice thing is our brain is sort of hardwired to understand a lot of this. There's a lot of psychology that goes into that. It's really kind of cool. But, right. Blah, 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 blah. Now, let me ask you this, though. Let me be really careful. What needs to be true about the 2 sets in consideration for this to really work. So I'm saying that the number, so let me call this set A, let me call this set B. So the number of things in A plus the number of things in B, I want that to equal the number of things in A union B. Is that just to get really technical for a moment, right? The only way that's true is if what? Okay, good. Meaning that A intersect B has to be, do it. A intersect B has to be 0, has to be empty. It's the empty section, yeah. Okay. So that's one level of things. Let me just tell you this and see your reaction. In fact, all of the basic operations we use, addition, multiplication, division, subtraction, they're all called binary operations. Anybody know why it might be called binary operation? What about 2? If I ask you what's 4 plus 7 plus 8, can you literally add all 3 of those at once? You cannot. You cannot. You with me? You can figure out the answer quickly, but that doesn't mean you did all of them at once. You can only add 2 things at a time, yes. So if I said what's 4 times 8 times 7, nobody in here is doing that all at once. You're doing 4 times 8, and then times 7, yes? So that is a binary operation. I have 2 inputs for 1 output. Okay, I like it. And I always wonder, I taught astronomy a few times, and a student told me, why are you making this so hard, man? I thought we were just gonna look at stars and shit. You're talking about right ascension and I'm like, come on. So it's really weird. I imagine somebody out there going, how the hell is this guy making addition so hard? What the hell? Okay. Hopefully it's not too much of that. So let's get into the difference. So I got set method, and this is a little side note. I've got the measurement model, right? Why do you call this method? This is a model. So all the measurement model is exactly like somebody said. The most primary, the most basic application of a measurement model is just the number line. So if I have 2, so I can represent 2, and then I go 4 more. 1, 2, 3, 4. So I go 4 more. Yeah, that's amazing. Then that's another representation that 2 plus 4 must be 6, because that's where I end up. And again, the chant method is actually sort of a measurement model in a sense, because you're kind of chanting the tick marks. Okay, nothing too crazy there yet. This is sort of a visualization of the idea of counting on. 2 plus 4, you start with 2, and then you count 3, 4, 5, 6, you count on 4 more. Very often you'll see a student do this: 2, 3, 4, 5, 6. So they make sure they count it on this many. Okay. Blah, 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 blah. Okay. Let me ask you this. Okay, let's talk about the properties of adding numbers. Let me just say a property here and see what your reaction is. Commutative property. Commutative property. I got a reaction over here, I'm not sure what it was. Commutative property. Does that sound familiar to anybody at all?
Yes.
Okay. What does it mean? I'm very honest. Shit. Yes.
Is that where you can switch the numbers around
Yes.
and still get same answer?
Does anyone live in this room? Where's he going? We all have to commute here, yes? So individual, I love it, enjoy that for a moment. Individual things commute. So when I have 2 plus 7, and I say that equals 7 plus 2, I have moved individual pieces of the problem, correct? Okay, I like it. I love that. Does anyone live here in this room? So if I say, so the first level property is commutative property. By the way, I don't care that much about it, but it's commutative, it's not communative. We're not making a bunch of little communes. So an example of that would be 2 plus 7 equals 7 plus 2. Let me do another example, it's a little more interesting. 3 plus 4 plus 9 equals 3 plus 9 plus 4. What actually moved? What actually moved from one side to the next? The individual numbers, 4 and 9, correct? Does anyone know what property that's sort of related to, but it's not really that property? There's another property that's... No. That would involve multiplication over addition, yeah. The first 3 letters sounds like you're gonna tell somebody off of it. Associative. Jeff, man, dad jokes, I love it. Associative, so commutative is when individual elements move. Associative is when parentheses get up and move. And the funny thing about both of these properties is it's just saying I can add numbers whatever order I want to. If I only have addition, isn't that on one level of PEMDAS? So I can do that whatever the shit order I want to. That's really all these properties are saying. So to make this become associative, it would have to be this. The parentheses would have to get up and move. So that's the easiest way to tell. I always say individuals commute, parentheses associate. Okay, this is all very fascinating. Does this sound at all familiar? Just to let you know, by the way, how do I say that? You get high enough in the math and you start talking about these different kinds of number systems, and some of them might not be commutative. Now, in our number system, addition is commutative. What is not commutative in our number system? What'd you say? Multiplication is commutative. What's not commutative? Subtraction. Is 7 minus 2 the same thing as 2 minus 7? No, one is the negative of the other one. And this, according to this book, negatives don't exist yet, so we're not there yet. You guys kind of with me? So multiplication and addition are commutative and associative. Division, subtraction are not. I like it. There's one little dude I skipped, which I feel really bad about, because it's one of my favorites. So the next property is called closure. Does anyone know like the psychological definition of closure? No? You ever heard of like if a relationship ends, you want to get closure? Okay. So that's not what this is. This is a mathematical idea. And I love this. In order for something to be closed, if addition is meant to be closed over whole numbers, when I add any two whole numbers, the answer has to be a whole number. So if I have a room with all whole numbers in it, and I combine two of them, and I get something that's not a whole number, I have to go outside of the room. I have to open the door. It's not closed. Does that make sense? So in order for some operation on a set to be closed, when I do the operation on anything in there, it has to stay in there. It can't go out of there, because then you have to open the door. It's not closed anymore. It's open. Does that make sense? So if I have whole numbers, somebody help me out. What the hell are whole numbers again? Where do they start at? No. 0, because what's the number that looks like a whole? 0. So 0, 1, 2, 3. If I subtract two whole numbers, must the answer be a whole number? We saw earlier, why not? What's 2 minus 7? -5. Is that a whole number? No, so is subtraction closed over the whole numbers? No, because I can subtract two, if I have all the whole numbers right here they all are, and I subtract two of them, do I stay in the room necessarily? No, because I could get -5, which is over here. Freaky dude, we put them over there. You kind of with me? Okay. I appreciate you guys saw already. Okay. So closure is one of my favorites because the word makes so much sense. So an example would be whole numbers are closed under addition. We'd say with respect to addition, because if I take any two whole numbers, A is an element of the whole numbers, B is an element of the whole numbers. Look at me using symbols you should know. A plus B must be an element of the whole numbers. So addition is closed because if I add over whole numbers, because if I add any two whole numbers, the answer is whole number. Now I'm asking this, is subtraction closed over the integers? What are integers? Does anybody remember?
It's any number?
No. It's whole numbers plus their negatives. So is subtraction closed over the integers? Can you subtract any two integers and get something that's not an integer? So basically, integers are just whole numbers and their negatives. So if you think I can subtract two whole integers and get something that's not an integer, it would have to be like a fraction or something. Can you subtract two integers, whole numbers and their negatives, and get anything that's not an integer? No, that's impossible. So that would be closed. Is multiplication closed over the whole numbers? If you take any whole number times another one, can you get anything that's not a whole number? No, that's impossible. What about division? Division immediately dies. What's 1 divided by 2? Is that a whole number? No, it's dead. What's 1 divided by 0? It's even worse. Right? Okay, so everybody get the idea of closure.
So that it stays just within that.
Yeah, if I give you a set, whole numbers, and I say, is addition closed? You have to think, is there any way to add two whole numbers and get something that's not a whole number? Do I have to leave the room of all whole numbers to get the answer? If I said subtraction in whole numbers, not closed. Because I have to go next door to the freaking negative numbers. They're not over yet. Yeah, okay, maybe. Okay.
Blah, 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 blah.
Okay. What about, how about this? Has anybody ever heard of the identity? Identity? Yes. It's a really good movie with John Cusack. But the additive identity. What's identity mean?
That might be too big.
What kind of class is it? Sort of. Like you have an identity, correct? Somebody could steal it, hopefully not. So identity is sort of like how we define ourselves. So if I have a number that I'm calling the identity, what I mean is, if I operate with that number, it does not change the other number, right? You guys kind of with it? So if somebody in the building, 3 buildings over, stumbles over their shoe because they forgot to tie their laces, does that change any of us right now? No. So that would preserve our identity. We wouldn't change at all, given that happened. So is there a number that I can add and it does not change the number I added it to?
0.
0. Cool. So the additive identity is 0. Just to look ahead, what's the multiplicative identity?
1.
Crazy sauce. Okay. All right, how we do? So later we'll get into multiplication. I'll talk about that again then. So here's something, let's see if this looks familiar. I'm not going to make this whole thing, I'm just going to make, this might not be what you thought it was. This is an addition table. So if we wanted to have students fill this in, what methods could they use to start filling this in? Yeah. So the adding 0. How do you feel about that? Adding 0 is a great place to start, right? There is a property that will help us. I only have to do a little over half of this. There's one property that will make it so I only have to do a little over half of this. And then I automatically have the other half. There's one property we talked about.
Is it right then?
No? Commutative. If I figure out what 2 plus 1 is, that must mean I know what 1 plus 2 is. You with me? So, not quite half of this gets so I can basically do this. So if I figure out what all this is, that only means I know what that is. By the way, there's a good picture of this in the book I'll show you in a minute. So one thing I could do is commutativity. So once I get part of this, I automatically have the other part. Adding by 0 is easy, so that's easy. Because that doesn't change anything. What's the next easiest column to fill in? Well, that's the 0. We already did the add 0. 1, yeah, because if I add 1 to anything, I just have to count one more place, right? So counting by 1. You could also go by 2, that's fine. Here's a good one. Everybody write this down for me. I want to know what 14 plus 873 plus 16. What would you do first? 14 plus 873 plus 16. Yeah, not just because they're the smallest ones, but because together they make a nice round number. Now later, this chapter they don't say this yet, but later we're going to call those compatible numbers. 7 and 3, 4 and 6, 15 and 5. They're compatible because once I put them together, it's a nice whole number. Whole numbers are the best thing in the universe to have involved in an addition problem, correct? Subtraction problem, not so much, but yeah, we'll get it. So I have the idea of combining to 10 is what they call it right now. But I'm going to tell you, it's actually called compatible numbers. Then you have doubles. Very often students kind of get the idea of doubling, and what I mean by that is 2 plus 2, 3 plus 3. So if you add something to itself, they kind of pick up on the fact that that just doubles what that thing is. And then you have adding 10, which is kind of like the next level up from adding 0. The easiest thing to add to anything is 0. The next easiest thing to add to anything is 10. Because that's a 0 in the ones place, right? You guys gonna follow? We're not gonna go up to 100, by the way. We're only going up to 10. For these poor little people. Blah, 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 blah. Yeah, and the last couple are kind of silly. Associative might come into play. How would associativity come into play? Well, it would come into play like this. If I had to do 9 plus 5, what do I wish was there instead of 9? It's almost a nice number. 10. I wish 10 was there. Well, what's 5? 5 is 1 plus 4. Correct? So 9 plus 5. Let me overanalyze the hell out of this thing. And by the way, I need you to understand, I'm about to do something that's overanalyzation for us. But dear God, it's necessary as hell for little people that have never seen this shit before, yes? So a lot of that's going to happen in this class. So this is 9 plus 1 plus 4. So I replaced 5 with another representation for 5. And then I can use associative property to do that. So then I get 10 plus 4, 14. last little dude that I'll talk about. Yeah, let's see if you guys like this. Doubles plus one. That's what it's called. Doubles plus one. Pretend like that word is doubles. This will be something like, if I have to do 7 plus 8, that's 7 plus 7 plus 1, which is 14 plus 1, which is 15. So that was not as common, but still, students pick up doubling pretty quickly. So if you can base it on doubling, they can get that part pretty quickly. So double plus 1 is nice because counting by 1 is easy, and doubling they get. Let me stop for a minute. Okay. What I find really fascinating right now is, have any of you guys even stopped to think about how much goes into just getting to where you are in terms of how you're able to work with numbers? Some of you guys might say, I suck at numbers, and I'm like, you're so much better than you were when you were 2. Okay. As far as I know, it could have been some crazy whacking the button. You're like, 7 plus 3 is 10. Instead of, I don't know. All right, let me show you the picture in the book, by the way, because my picture, understandably, sucked pretty bad. So here's what was happening. Yes. There's the idea of commutativity, that kind of like, if I know what 1 plus 2 is, then that means I know what 2 plus 1 is. Yes. And then you've got this list of stuff we went through, and they kind of like fill it in as they go, so you kind of follow along if you want to. Not necessarily the most important thing in the world, by the way. If you see this diagonal here, this one here, you guys know what that is? That's doubles. I love it. Okay, cool. All right, so you can kind of pick out of this. So instead of just pure memorization, which is basically almost always the worst thing in the universe, you're trying to show them how things build on each other. Don't just memorize that 5 plus 6 is 11. Have a way to get there so you buy into it more instead of, that's what they told me it was. Okay, blah, 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 blah. Let me show you this. This is getting a little bit ahead, but I want to show you an example based on stuff we've done before. Can you guys take a minute and represent each of those numbers as so many flats, so many longs, so many units? What's a flat represent again? 100, because it would be 10 by 10, so it represents 100. You don't have to draw all the little things, just a flat, just a square, yes? A long is just a, right? Just a rectangle. Okay. So represent 117, 35. Okay. So what's 117?
Flat.
One flat?
One strip.
One line? Yeah.
And then 7 ones.
And then 7. 1, 2, 3, 4, 5, 6, 7. This poor little dude. Let's suck you in there. Okay. And then 35, of course, would be 3 longs and 5 units. So this is kind of, so when I had my squiggly line and the infinity symbol and the circle and all that kind of crap, this is the next level up from that. This is saying, we still have stuff for counting, but now the flat means we've counted 10 tens, and the long means we counted 10 ones. So this is kind of like organizing it better, because I don't want to draw 117 different shapes. So when I combine these together, what do you get? You get a flat, you get 4 longs, and you get how many units? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Just to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then what can you do? Good. So I can take 10 of these bad boys and make what out of them? A long. I like it. So I have 1, 2, 3, 4, and then this will make 5. And then I'll have how many? 2. So then what number is this? 152. Cool. Which is what 170 plus 35 is. Thank the gods. Okay. Are there other ways to represent addition? Oh God, yeah. And I'm hoping that you guys kind of bring that kind of creativity to your own classrooms. It doesn't have to be shown in the same way because the concept is independent from how we show it. So one reason why I love that we have so many teachers and so many perspectives is because some students will key on different perspectives better than others, right? And you guys have experienced this. You with me? You guys have taken teachers that not a word they say makes sense. Maybe that's happened to you right now, and I'm really sorry. And then you've had other teachers who like you completely 100% jive with what they're talking about. Yeah. Last 2 little things about addition, and then I want to show you some. Well, no, and then I'll talk about subtraction. Then we'll watch some videos of the little people. See if we see some of our favorites come back. Right? The little people show. If I ask you, what's 42 plus 18? And I want you to use associativity and commutativity to do that. If you're just learning this stuff, how could you break that up to put it together? So you haven't learned yet. For example, carrying 1. Not difficult. We could all do it. Learning what carrying 1 means and why it's important. Difficult. It doesn't make immediate sense. So we don't know that yet. We're not there yet. I don't know about carrying 1 yet. So who's got what? Yes?
Separate it by the place values, so like 40 plus 10.
Good.
2 plus 8.
Well, let's see. Well, first I got to do this. I want to see 42 is this, right? And 18 is 10 plus 8. Keep it as round as I can. So I haven't used the property yet. I've just rewritten what the numbers are in different names. 40 plus 2 is another name for 42. What property can I use now? To be technical, I would use associative and commutative, right? So I could do, how do I want to, well, so I want to move the parentheses so they're around 2 and 8, and I want to move the 2 and the 8 so they're together. So I can use commutativity and associativity at the same time. Make this 40 plus 10 plus 2 plus 8. And then, not surprising, you get 50 plus 10, and you get 60. Which is very often surprising to students, because they think 40 and 10 is 50. How the hell do you get 60? Well, because we got extra shit, right? And we do that all the time. 42 plus 18, you think it's 50. You do that in your head all the time. I know you do, because I do too sometimes. So, just gotta remember the carry on. So then something a little more simple. What if I had this? All I need to use is associative. Yeah, so I want these parentheses to move to be over here, yes? So then I just move them because I know that associative is a thing. And this, if we wanted to, we could do the same kind of stuff we did up here, or we could just realize 16, 10, 77, 3 is 10, so I get 8. What's 80 plus 21? 101. Yay! Okay, very fast learner. So, with all of this in mind, I know you know base 10. So do this for me. Using the same stuff we just did. Exactly the same stuff for exactly the same reason. I'm like, whatever, man. I ain't got 7 figures. Keep on. example, real quick guys, why would we put 2 and 8 together? If I had them in a big string of things to add, why would I put 2 and 8 together? Because they make 10, right? Sort of like we saw earlier, when I had 9 plus 5, and I took a 1 off of the 5 and made it 10, so then it was easy to do, 10 plus 4. Think that way. Why is 9 plus 1 10 in base 10? Because 9 is the highest single digit. If I add any more, I've got to go to the next place, right? So what's the highest single digit in base 7? 6. So once I get to 7, roll it over. Yeah? So when you're adding a bunch of numbers together, you're looking for the things that make it round. So to see 14 and 16, I'm like, kick ass. Let me put those together. Because I want to make it equal to my base. So what am I looking for here? I want to make it equal to my base. So how am I going to break 4 base 7 up? Considering I want to make 5 base 7 plus 7 become my base. So again, I mean, really, we're in base 10. Why do I look for 2 and 8, 4 and 6, 5 and 5? Why do I look for those? Because they become my base, which I know I can write as 1, 0. Nice round number. What's our base here? So what do I want to have happen? I want to break 4 up so I can add part of it to 5 to make it become 7, which in base 7 would be 10, because just like our base, right? So how do I break 4 up? 2 plus 2. I don't know why that 2 is so tiny, poor little guy. And then I use associated, 11. And like we just said, this is for the same reason that 8 plus 2 is 10. For us, 5 base 7 plus 2 base 7 is 10 base 7. So when do we roll over to the next place? Anytime we hit what we call 10, which is the number right after 9. So when will I roll over in base 7? When we hit what we call the number 7. Then I'm going to roll over. So in base 10, we look for things that add to 10. In base 7, we look for things that add to 7, because how would you write 7 in base 7? 1, 0. So in base 7, 7 is 10. Stop for a minute. There's somebody out there's like, I never thought I'd hear that sentence in my entire life.
7 is 10.
Yes.
Can you show how you did the last part again?
You mean from here to here?
Yeah.
All right. All right. What's 18 plus 1? And then what's 19 plus 1? 20. So I roll to the next place when I hit our base, right? So 5 base 7 plus 1 base 7 is 6 base 7. 6 base 7 plus 1 rolls to the next place. It's 1, 0. So let me really analyze the shit out of this. How do I take base 10, 7, right? Base 10. What would that look like in base 7? 1, 0. So what is 6 base 7 plus 1 base 7? 10 base 7, 11. Which we understand, like if somebody says, la corbeille, that is French for the wastebasket. It's my favorite little word. La corbeille sounds, ooh, and there's a wastebasket. When somebody in base 7 says 10, we know they mean 7 to us. But to them, it's freaking 10. Same reason. 9 plus 1 is 10. Ooh. 9 plus 1 equals our base. 6 base 7 plus 1 base 7 equals their base. So what is 5 base 7 plus 2 base 7? 10 base 7. What is 4 base 7 plus 3 base 7? 10 base 7. Okay. Let me stop for a minute. You all know when you have to add a bunch of numbers, you look for the shit that makes a 0 at the end. You just do. We all do. Of course we do. Why wouldn't we? Because that goes right with our base. We look for 14 and 16. We look for 18 and 12. We look for that stuff. If I'm in base 7, I'm looking for things to add to be 7 for the exact same reason. And then I count 1 from there. So is everybody cool with 5 base 7 plus 2 base 7 is 10 base 7? And again, 5 plus 2 is 7. And how do you represent that in base 7? 1, 7, 0 ones. Right, from your perspective. So that's why 7 is 10 in base 7. So what's 5 base 7 plus 4 base 7? Well, it's 2 extra. On top of the 2 I need to become 10. So of course it's 12 base 7. It's just 2 extra. Sort of like if I said, what's 15 plus 7? Can't you do 15 plus 5 plus 2? Isn't that a smart way to do it? I'm sure some of you guys do that. Yes? So that's exactly what we would do with this one. We'd say, all right, 5 base 7 plus 4 base 7, that's 2 more than what it would take to make it 10. So of course I end up with 12. Okay, you all really like that. Okay, so what about this here? Yeah, Jeff, another example. All right, so let's do 11 base 13 plus 5 base 13. Oh, is that a little too much? No, that'll be all right. Yeah, that'll be. This is a little tricky. This is trickier than I wanted it to be honest. Alright, let me try it. This is not exactly what I wanted it to be. Let me go for a smaller number. 4 base 5 plus 3 base 5. There we go. Let's try that. I don't want to be that tricky. This would just be 16 base 13. Now it didn't do what I wanted to do because I wasn't thinking. So what am I looking for here? What am I trying to make happen? What number do I want to show up? 5. So then you could show yourself how much extra there is in 3. Or you can just realize how much extra there is and see what the answer is going to be. So if I show myself, how much do I want to pluck off of this 3? 1. This together makes what? 10. So then I end up with 12 base 5. Yeah. So from the beginning you can say 4 plus 1 is 10, as everybody knows. 4 base 5 plus 1 base 5 is 10. And I have 2 extra, so of course I get 12. Yes? Okay, maybe. Okay. Is that better? Okay. Okay. So let's talk about subtraction a little bit, and then I'll show you some videos. Yes? So, all right, let me do this. So base 10, 9 plus 1 is 10, right? 8 plus 2 is 10, so forth. Base 9. The highest single digit in base 9 is 8. And why do they start here? What's the highest single digit in base 10? 9. So of course if I add 1 to it, I have to go to 2 digits now. So the next place where I have to go to 2 digits in base 10 is 9. If I do 1 more on top of that, so what's the highest single digit in base 9? 8. If I add 1 more to it, I have to go to the next Now let's check it. What is 8 plus 1? 9. And how do I represent 9 in base 9? 1, 9, 0, 1. Whenever I hit the base, that's 1, 0. Correct? How do I represent 5 in base 5? Base 5. Yes? How do I represent 48 in base 48? 10. Great. Base 40. How do I represent 10 in base 10? 10. So how do I represent the number in the base of that number 10? Because it would take 148 and no 1s to make 48. It would take 110 and no 1s to make 10 in base 10, right? So all this symbol means is, hey, you made it to the base. So if I'm at 4 and my base is 5, I just have to add 1 to make it to the base. So then that's 1, 0. So if I have extra shit, so if I have 4, all it takes is to add 1 and I'm at 10, I'm at the base. And how much extra do I have? 2. So of course it's 12 base 5, I have 2 extra. Same way you would add 18 plus 6. You go, okay, it takes 2 to get to 20, 4 extra, 24. That's another way to add 18 and 6, yes? You add the part that gets you to the next whole number, and then you add what you got left over. Is that cool? Does anyone do it that way ever? Some of you guys do? Okay. The rest of you guys are like, I got a calculator on my phone, man. What do you want? Okay, I understand. All right. Is that at all better? And trust me, one thing I need you to take away from us continuously going to different bases. Can somebody remind me why we do that? What's one fundamental reason we do that in this class? Why do we go to different bases to discuss ideas?
To kind of put ourselves in
Yes.
their shoes.
To put yourselves in the shoes. Now you could be teaching a level, which I forget exactly where it happens. 17. You could teach a level where you do talk about different base numbers. But I'm talking about first, second grade, right? I'm talking about when they're just learning numbers themselves, third grade, whatever. When you start getting up there, you start to add stuff. You put yourselves in their shoes. This is all new shit. Base 7. Before this class, did anybody ever use base 7 before? All right, that was brand new shit to you. You were just like a little human coming along. What is this? So, as a teacher, it's better to be able to connect with how your students are feeling. The worst thing in the world is to be a teacher that's like, well, this is easy stuff. You know, you can do this stuff. What are you talking about? You should be able, I could do this. I could do this. Well, you can't think back to when you were freaking 5. You can't remember what that was like. Okay. We all have memories of when we were 5, but we don't remember what it was like to be 5. That's something we can't remember. Okay. So subtraction. Take a moment. Let me do something different here. Take a moment. Can you come up with kind of a word problem where a student would have to use subtraction? Somebody's doing selfies out there. Okay. Yes.
Sally has 4 cookies and she eats 2 of them. How many cookies does she have left?
Beautiful, right? Sally has 4, she eats 2. How many does she have left? Let me write that down. Sally has 4 cookies. In an immense show of willpower, she only eats 2. How many left? How would you represent this visually? Like drawing, because you could bring cookies in, yes? That's dangerous for me. I never want to play like the poker with the Oreos because my pot keeps shrinking over time.
Bullshit.
Sorry, who had a hand up? What did I ask? How would you show this visually on a piece of paper? Yes. Literally take away. Okay. So this is not surprisingly this word problem would lead to the idea of takeaway. So one of the primary ways we think of subtraction is takeaway, which makes sense. That's the immediate first thing we would think of. I had this many, somebody took this many, how many do I have left? That's taking away, right? Does somebody have a different idea that would not use take away? It uses something else instead. So this is an example of the takeaway approach. Who's got maybe a different type? Yeah.
Going backwards on number one.
Let's do it again.
Going backwards on number one. Like starting, like taking.
Oh, so the same 4 minus 2, but so you start at 4 and you go back 2. Okay. So that's a measurement model, but what would get me there? And that's kind of like, I need you, so if I go to 4 and I go back 2, that's still taking away. That's still the idea of taking away. But I like it. That's kind of like this would be more set, yours would be more measurement model. I love it. Sorry? Eliminate sort of sounds like take it away, right? Okay.
Well, it's not gonna fit something.
Eliminate?
Yeah.
So what do you mean by that? Sorry.
Like, if you draw 4 cookies on your paper, and then you exit to.
Oh, okay. You are kind of taking them away in a different way. Yeah, I got you. So I like that you're all like, dude, what do you want from me? That's what subtraction is. What about Sally has 4 cookies, Fred has 2. How many more cookies does Sally have? Did I take any cookies away? So what am I doing? I'm taking Sally and Fred, and I am comparing this. That's called comparison. I love it. So you have, that's the takeaway approach. Sally has 4 cookies. Hayes? Sure. Sally Hayes, 4 cookies. I teach math, I don't know. Sally has 4 cookies. Fred has 2. How many more does Sally have? Now, listen. I want to address this because we're going to do this a lot. This is going to happen a lot. Some of you guys right now are probably thinking to yourselves, it's the same damn thing. It's 4 minus 2. What the shit, dude? When you are first learning this, those are 2 completely different physical situations, correct? There's no reason that we should automatically understand that they lead to the same math. Does that make sense? We know they both are 4 minus 2. Little people, no idea. Why would it be? They're 2 different situations. One, she's eating. The other one, she's looking. Why would that be the same math? You guys gonna follow? So you have to be very careful about taking your own understanding of something and trying to broaden that out because they're not gonna have that understanding. Okay. So this is what's called the comparison approach. Does anybody think they have another one? Out of curiosity?
Would it be like maybe has 5 apples and 2 are rotten? How many can she eat?
Oh, I see. It's still kind of takeaway though, but I like it. All right, so this is a little tricky. I understand. Just want to throw it out there. What about this? So comparison requires 2 different situations, 2 different people, correct? This sort of feels like comparison, so I don't blame you for feeling this is the same, but it's not really. Sally has 4 cookies. She wishes she had 8. How many more would she need to get there, right? Or I have to walk 5 miles. I've walked 2 miles so far. How many more miles do I have to go? So I'm not really comparing 2 different people or something. This is what's called, let me see. So let's look at that last thing I said. I have to walk 5 miles. I have walked 2 miles so far. How many more do I have to walk? Do you guys see how that's, is that really only based on subtraction? Or do you see how that's related to addition? How would you reword that more simply? I have 5 miles to walk, I've walked 2. How much further do I have to go? How would you rewrite that just as a addition problem? Maybe where something's missing. Yes?
Blank plus 2 equals 5.
Say again?
Blank plus 2.
Good. Blank plus 2 equals 5. Yes? You guys with me? So not surprisingly, this is called the missing addend approach. We call the things involved in an addition problem, we call them addends, or sometimes we call them summands. How important are those words? Not. But it's that addend approach. That's a more important word, but it's the missing addend. So I have to walk 5 miles. I've walked 2 miles. How much farther until I just call Uber? How much farther do I have to go? That is literally 2 plus what equals 5. Now the funny thing is, that's the last one I did, but this is actually where you start. So, when you start talking about subtraction, what will you have finished talking about? Addition. Whenever you're about to start a new thing, you try to directly connect it to what they just did. So they know 2 plus 3 is 5. Therefore, they could more easily handle 2 plus what is 5. They can go 3. And then you start to try to show them, okay, that's related to this new thing called subtraction, right? So you give them a bridge between what they know and what they're about to learn. A bridge. So this is a great thing to do immediately after you finish talking about addition. You do missing add-in because it builds on addition. You don't even have to use the subtraction symbol yet. So this is called the missing add-in. Part of me wishes we would just put X there and get them to understand algebra earlier, but that's fine. Whatever, Jeff. You're weird. Okay. Okay. Blah, 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 blah. So, we can also look, just like somebody said earlier, let me make sure I don't want to say anything else about it. Yeah, let's do this. Let's look at each of those a little more carefully. So, takeaway approach. So, I could do a set method. So I want to do 4 minus 1. I can have 4 things, and I literally just take 1 away. So then I'm left with 3 things. It's crazy. A little existential bowling ball. So then they can just count and see the answer is 3. It's crazy. Okay, so that's takeaway approach. Set method. What about takeaway approach measurement model? I keep saying method. This is the set model. Starts with an M, gets me confused. What about the measurement model? Somebody else brought that up earlier. What would you do to illustrate the same problem, 4 minus 1?
You start at 4 and you...
Yeah, so you take 1, 2, 3, 4. You start at 4. And then you just go back 1. So you take 1 away from the progress you've made. So you can see you end up at 3, right? Amazing, okay. So let me get really hyper-technical for a moment. If we have sets A and B, the number of stuff in A is little a, the number of stuff in B is little b, and B is a subset of A. Then A minus B is the number of things in A minus B. Do you remember how I told you that remember Cartesian product, anybody? Where you make pairs of stuff between two? And I said that's where we stole the symbol for multiplication. We did something similar with that minus symbol. It was originally for sets. You take everything out of A that's also in B. That's what that means in set notation. And we stole it to be the symbol for subtracting numbers, right? Okay, y'all look appropriately sized. So a concrete example of this. Can somebody give me, so if my set A is A, B, C, D, can somebody give me a set B that follows this restriction? Sorry, B? C. Okay, let's just say. Does that follow what needs to happen? I could have accepted the whole damn thing, but then, that would have worked too. So how many things are in A? Crazy. How many things are in B? Holy shit. What is A minus B? So this is not minus in terms of numbers, this is set minus. So take everything out of A that is also in B. The AD. How many things are in there? And sure enough, 4 minus 2 is 2, right? That's literally the concrete thing of what all this shit here means. So if I have two sets, one is a subset of the other, then the number of things in A minus B is equal to the number of things in A minus the number of things in B, A minus B. Maybe. So I don't know if you remember, that minus symbol with sets did not mean the same thing exactly as minus means with numbers. You guys remember this? But this is what makes it become the minus thing with numbers. Okay. You guys are doing good. One of my favorite comedians, he'll every now and again will say, "We're having a good time. We're having a good time." Yeah, you are. So here's the last thing I'll talk about, then we'll watch some videos. 4-fact family. Am I running out? So here's an example of a 4-fact family. You guys help me out. What is 4 plus 5? 9. Holy shit. So what's 5 plus 4? 9. So what's 9 minus a part of it? The other part. What's 9 minus the other part? The other part, right? That is a 4-fact family. So the first two are an illustration of what property? Commutative. These two are kind of nifty. These are the two that are, if I have a total minus one chunk is the other chunk. That's all it says. 10 minus 2 is 8. 10 minus 8 is 2. 10 minus one chunk is equal to the other chunk. Right? That's all those last two say. So you can call it the chunk property if you want. So let's watch some videos of little people using all this stuff. So it means I have to turn you off.